Imagine waking up one morning in Florida, sipping your coffee, then stepping aboard a vehicle shaped like a massive silver bullet. Just 90 minutes later, you arrive in New York City in time for your first meeting of the day. A journey of more than 800 miles compressed into the length of a short movie. That is the ambition behind China's proposed 620-mile-per-hour ultra-high-speed train project. And if the technology performs the way its developers hope, it will not simply break speed records. It could fundamentally reshape how humans travel between megacities while creating direct competitive pressure on domestic air travel itself. As an investigative journalist, I usually approach extremely ambitious technological claims with a healthy degree of skepticism. But what makes this project especially interesting is that it no longer exists only as a concept on paper. For more than a decade, Western countries pursued their own futuristic transportation projects. Elon Musk promoted the idea of Hyperloop. Germany developed the Trans-Rapid system. Japan pushed Maglev technology beyond 370 miles per hour years ago. But many of those projects eventually slowed down because of cost, infrastructure complexity, and the brutal realities of real-world deployment. China, however, continued pursuing the concept at a national scale. Instead of simply optimizing traditional steel wheel rail systems, Chinese engineers began attempting to move beyond the physical limitations of that model entirely through magnetic levitation and low-pressure transport environments. That is why this project is attracting so much attention from engineers around the world. Because the question is no longer simply, how fast can a train go? The real question is which country can actually transform that technology into functioning infrastructure at scale. And to understand why the 620-mile-per-hour threshold matters so much, we need to examine the two biggest limitations rail systems have faced for more than a century: friction and aerodynamic drag. For decades, the world relied on steel wheels running across steel rails. From Shinkansen in Japan to the TGV in France, nearly every high-speed rail network encountered the same physical limitations. As train speeds approach roughly 220 miles per hour, vibration increases dramatically, while air resistance becomes an enormous barrier. And pushing beyond that point requires exponentially more energy for relatively small gains in speed. That is why Germany, France, and Japan eventually settled around the range of 200 to 220 miles per hour for commercial operation, not because they lacked engineering capability, but because they realized that continuing to force steel wheels through dense atmosphere at higher speeds becomes increasingly inefficient, both physically and economically. And that is where China's approach began to diverge from everyone else. Instead of continuing to optimize traditional rail systems, Chinese engineers shifted towards something called T-flight, a transportation system combining magnetic levitation technology with a low-pressure tube environment similar to the Hyperloop concept. In Yangao County, the CASIC, an organization historically focused on rockets and aerospace systems, constructed a large-scale vacuum test track designed to eliminate most aerodynamic drag. In July 2024, a roughly 1-ton experimental vehicle successfully levitated approximately 9 inches above the track using magnetic fields alone. By early 2025, multiple reports suggested the system had already reached speeds near 400 miles per hour, with some short acceleration tests reportedly approaching 435 miles per hour. To understand why that matters, remember that the current manned Maglev speed record still belongs to Japan, where the L0 series reached roughly 375 miles per hour back in 2015. Of course, some caution is still necessary here. Japan's system involved a fully manned train operating across a test track more than 25 miles long, while China's T-flight system remains in earlier stage testing with lighter payloads and shorter distances. But what is attracting engineering attention is not merely the speed itself. It is the technical philosophy behind the project. And what makes this even more fascinating is that the West once had an opportunity to pursue a very similar direction more than a decade ago. Back in 2013, Elon Musk unveiled the Hyperloop concept with ambitions of reaching speeds around 750 miles per hour. Silicon Valley exploded with excitement. Hundreds of millions of dollars flowed into startups like Virgin Hyperloop and Hyperloop One. But by late 2023, Hyperloop 1 had shut down operations entirely. Most Western Hyperloop projects ultimately stalled at demonstration systems and short prototype tracks. And the difference was not simply money, it was the way each system approached the same problem. American startups were forced to convince investors through rapid commercialization timelines and short-term profitability expectations. China, meanwhile, treated T-Flight as a long-term national infrastructure project potentially spanning decades. The second major difference involved the engineering strategy itself. Musk's Hyperloop concept pursued an environment approaching near-total vacuum conditions, extremely expensive and extraordinarily difficult to maintain at large scale. China instead adopted what engineers describe as a low-vacuum approach, accepting a small amount of remaining air resistance in exchange for lower infrastructure costs and greater real-world practicality. At the same time, Chinese engineering teams also began developing new vacuum-resistant materials, high-temperature superconducting systems, and hybrid suspension platforms supported by artificial intelligence designed to manage vibration at ultra-high speeds. That is why engineers around the world are watching this project so closely. Not because China is simply building a faster train, but because it is attempting to solve a transportation problem many experts once considered too difficult or too expensive to deploy in the real world. And perhaps that is the biggest difference between the two approaches. Elon Musk introduced a bold and inspiring idea. China is attempting to turn that idea into functioning infrastructure. When we look toward Europe, the contrast becomes even clearer. While China and Japan continue pushing toward speeds between 375 and 620 miles per hour, major rail systems in countries like Germany and France still operate primarily around 180 to 220 miles per hour using traditional steel wheel technology. And what makes this especially interesting is that much of the Maglev foundation China is developing today actually originated in Germany itself. Beginning in the 1980s, the Trans-Rapid project demonstrated that magnetic levitation trains could operate stably at extremely high speeds across test tracks extending more than 18 miles. But Germany ultimately never commercialized the technology at large scale. High costs, prolonged political debates, and the conservatism of existing infrastructure systems gradually slowed the project down. There is even a famous phrase often repeated among European engineers: Germany invented Maglev, China decided to build it. And perhaps that captures the biggest difference in this race. One side focused on proving the technology could work, the other focused on transforming it into national infrastructure. However, as someone working in investigative journalism, I think it is equally important to confront the real-world problems hiding behind these impressive numbers. The first issue is economics. Even the existing Shanghai Maglev, only about 19 miles long, has reportedly struggled financially for years. So if these systems expand into networks stretching hundreds or even thousands of miles, the costs could become enormous. How expensive would tickets actually be? Could ultra-high-speed rail truly compete with commercial aviation on a large scale? Those questions remain very open. Then comes safety. At speeds approaching 620 miles per hour, even tiny irregularities inside a low-pressure environment could potentially create catastrophic risks. Pressure chambers, emergency barriers, and advanced sensor systems sound impressive in theory. But so far, no country has yet operated a full-scale, ultra-high-speed vacuum transport network commercially in the real world. And finally, there is geology itself. Maintaining a low-pressure transport tube stretching thousands of miles across regions vulnerable to earthquakes, shifting terrain, or structural instability remains an enormous engineering challenge, even for the world's most advanced infrastructure systems. But after looking at the entire picture, what interests me most is not simply whether China eventually reaches the 620-mile-per-hour milestone. It is why China continues moving forward, while many similar projects in the United States and Europe slowed down or stopped entirely. And perhaps the answer is not purely technological, because Maglev technology has existed for decades. Japan exceeded 375 miles per hour back in 2015. Germany developed Trans-Rapid years earlier. Elon Musk introduced the Hyperloop concept in 2013. The real difference may lie in something else entirely. Who is willing to pursue the idea long enough, and at sufficient scale, to transform it from an engineering concept into functioning transportation infrastructure? China currently holds one major advantage: a system capable of supporting massive infrastructure investment across decades, even for technologies that still carry enormous risks and have not yet proven long-term profitability. Of course, that does not guarantee success. History is filled with ambitious transportation projects that ultimately struggled economically. The Concorde is one famous example, and T-Flight could eventually face many of the same questions. But what makes this story especially interesting is the pattern surrounding many of China's large-scale infrastructure projects. When they begin, the world's first reaction is often skepticism. The same thing happened with China's high-speed rail network more than a decade ago. Today, it has become the largest high-speed rail system on Earth, which means this competition may no longer be simply about which country builds the fastest train. It is increasingly becoming a competition over which nation is willing to invest enough capital, commit enough time, and absorb enough risk to shape the next generation of global transportation infrastructure. And right now, China is clearly attempting to position itself at the front of that race, even if the financial costs and engineering risks could become enormous. Perhaps the future of transportation will no longer belong entirely to overcrowded airports and short-haul flights filled with delays and security lines. It may gradually shift toward ultra-high-speed ground transportation systems capable of shrinking the distance between megacities into only a few hours. That is the vision China is pursuing with T-Flight. But the biggest question still remains unanswered. Will technologies like this truly transform global transportation, or will they ultimately become another generation of overly ambitious experiments? And if ticket prices eventually became competitive with airline travel, would you personally step aboard a train traveling nearly 620 miles per hour? Leave your thoughts in the comments below. I would genuinely love to hear what people think about the future of ultra-high-speed transportation. My name is James. I started this channel during one of the most difficult periods of my life after losing my job 2 months ago, hoping to rebuild everything from the ground up and support my family. If you find value in these videos, please consider supporting the channel by liking the video and subscribing. Your support truly means a great deal to me, and I will see you in the next investigation.